In this section, we will discuss how physical activity can be measured, as it is a far more complex construct to assess compared to fitness. You have all taken exercise prescription courses and are familiar with measuring cardiorespiratory fitness, such as VO2 max, as well as body composition and muscular strength using both field-based and laboratory-based methods. However, measuring physical activity is more complex than measuring fitness for several reasons. PA varies from day to day and is constantly changing. In addition, there are multiple ways to quantify PA, such as energy expenditure, duration, step counts, or heart rate. Furthermore, PA is a multidimensional construct that includes components such as duration, intensity, frequency, and context. Without a valid and reliable measure of daily or weekly physical activity, epidemiologists would be unable to evaluate the association between physical activity and the risk for chronic disease. In addition, measures of physical activity are needed for the descriptive epidemiology of physical activity, such as the assessment of variation in physical activity by age, sex, race, ethnicity, health status, and geographic location. We will discuss the pros and cons of different measures, how to choose outcome measures, and how to select appropriate instruments for various study samples, purposes, and settings. We will examine various lab and field methods for measuring physical activity, such as self-report, pedometers, heart rate monitors, and advanced methods like doubly labeled water. We'll also consider the trade-offs between feasibility and validity, the type of raw data each collects, and what physical activity dimensions can be measured. This figure illustrates the relative feasibility and validity of different physical activity assessment methods. In general, methods with higher validity tend to require more complex procedures and specialized equipment, making them less feasible for use in large populations. As a result, the trend in the figure moves downward as it shifts to the right, reflecting a trade-off between feasibility and validity. The choice of physical activity assessment method depends on your research priorities. Epidemiologists typically prioritize feasibility over accuracy, especially in large-scale studies such as cohort or surveillance studies, which involve large populations. In these cases, methods that are practical and scalable are often preferred, even if they are less precise. In contrast, exercise physiologists tend to prioritize accuracy over feasibility. For detailed, mechanistic, or laboratory-based studies, more precise measurement methods are preferred, even if they are more complex and involve smaller sample sizes. Self-report instruments for assessing physical activity include PA diaries and various recall questionnaires. A PA diary involves recording physical activity hour by hour over several days, similar to a 3-day diet record. Although it is still a self-report method, it tends to be more accurate because it reduces recall bias. PA questionnaires can be categorized based on intensity, such as moderate or vigorous activity, or by domain, such as leisure time and occupational activity. Self-report measures are the most commonly used methods in adult populations. However, they present notable challenges when used with children. Overall, they are the most feasible and cost-effective approaches, making them widely used in large cohort and surveillance studies. These survey-based tools require active participation from individuals and are commonly used for population-level physical activity surveillance. The advantages of self-report measures are clear. They are easy to administer and do not require extensive expertise to process the data. Most importantly, self-report methods provide rich contextual information about physical activity, such as the type of activity and the setting in which it occurs. However, there are several limitations. Cognitive constraints can make it difficult for children to complete many self-report instruments. Children may also struggle to accurately describe intermittent and sporadic activities. For example, while adults can often recall a 30-minute jog, it is much more challenging to characterize the varied and unstructured activities children engage in during recess. In addition, children tend to over-report their activity levels, often to a greater extent than adults. Although this is partly due to recall difficulties, it is also influenced by the design of many self-report instruments, which may not be well suited to capturing children's activity patterns. Self-report validity is a concern. NHANES data shows a significant discrepancy, with self-report indicating over 60% of U.S. adults met PA guidelines, while accelerometry showed fewer than 10% met them. Estimates vary substantially depending on the measurement method. To summarize, self-report instruments continue to play an important role, particularly in large population studies or intervention trials, where it is difficult to collect objective data from large samples, especially among children. Self-report measures can provide rough estimates of physical activity patterns, but they are best used in combination with objective measures. While it is often difficult to determine which instrument is the most accurate, obtaining consistent results across multiple methods can significantly strengthen the validity of study conclusions. Then, let's take a look at the pedometers. Pedometers are probably one of the most common tools for measuring physical activity and have been used for a long time. It only measures step counts, which is easy to interpret. In terms of placement, pedometers can be worn in different locations. Traditionally, they are placed on the hip. Some models can be worn on the ankle, and nowadays, devices like Fitbit and Apple Watch track steps from the wrist. However, reliability and validity can vary depending on the model, brand, and population. For example, in stroke patients or individuals with limited or altered walking patterns, pedometers may not be very accurate. There are also some measurement errors. For instance, some studies have reported that devices may count steps while a person is riding a bus, even though they are actually sitting still. One major advantage is that they are inexpensive. You can get one for around $20, and they can still do a decent job compared to more expensive devices. They're also small and non-invasive, so most people won't even notice them when worn on the belt. They are easy to use and interpret. Everyone understands what steps mean, and generally, more steps indicate higher physical activity. Even early pedometers provided real-time step feedback, which supports self-monitoring and behavior change. You've probably heard of the 10,000 steps per day recommendation. This idea originally came from Hitano in Japan. Their study used pedometer as a measurement tool. However, there are also limitations. Pedometers mainly capture walking or other locomotor activities. They are most accurate at moderate walking speeds and less accurate at very slow or very fast speeds. They also don't provide detailed information about frequency, intensity, or duration of activity. In addition, the data can sometimes be manipulated. For example, children may shake the device to increase step counts. There's also something called reactive, where people become more active simply because they know they are being monitored. To summarize, pedometers have strong potential for use across a wide range of populations. They can serve as primary outcome measures, as criterion measures to validate other instruments like self-report, or as complementary tools to allow triangulation across multiple measures. In physical activity intervention studies, pedometers are often used to assess out-of-laboratory activity. However, accelerometers are more commonly used today due to their greater precision. Pedometers also work well as a physical activity promotion tool. They are especially effective for encouraging inactive individuals to become more active, particularly at the beginning, possibly due to the reactivity effect. Heart rate monitoring measures the body's physiological response to activity, rather than the activity itself. Traditionally, heart rate is measured using a chest strap that detects electrical signals from the heart and transmits them wirelessly to a wrist receiver. More recently, wrist-worn devices like Apple Watch and Fitbit use photoplethysmography, or PPG. This method uses light, typically green light, to detect changes in blood flow and estimate heart rate. Heart rate monitoring is based on the relationship between heart rate and oxygen consumption during aerobic activity. As activity intensity increases, the body requires more oxygen, and heart rate rises to deliver it. This makes heart rate a useful tool for prescribing exercise intensity, such as using %HR max or heart rate reserve. However, heart rate can be influenced by several factors, including temperature, hydration, activity type, training status, and age. For example, maximal heart rate generally decreases with age. Heart rate monitoring is commonly used in athletes, such as cyclists, to assess training effects. It provides information on intensity, frequency, and duration of activity, and data collection is relatively easy. Participants simply wear the device. Because of the linear relationship between heart rate and VO2 during aerobic activity, heart rate can also be used to estimate energy expenditure. It has been widely used in research with children because it captures minute-by-minute physical activity data. However, there are several limitations. First, heart rate data need to be converted into meaningful outcomes, which can be challenging for interpretation. Second, traditional chest strap monitors may experience signal interference from electronic devices, potentially leading to data loss, although this is less of an issue with newer wrist-based technologies. It can also be burdensome for participants, as wearing a chest strap for long periods may be uncomfortable. Wrist-worn devices have reduced this issue. In addition, heart rate monitoring may be less accurate for individuals with hypertension or those taking blood pressure medications, and it is generally less reliable during resistance training compared to aerobic activities. To summarize, heart rate monitors are well suited for structured exercise settings, but traditional chest strap monitors are less useful for free living activity. However, newer wrist-worn devices using photoplethysmography, such as Fitbit and Apple Watch, have improved this limitation. Recent research suggests they provide reasonably accurate estimates in free living conditions. As mentioned earlier, the strong relationship between heart rate and energy expenditure makes heart rate monitoring a feasible tool for estimating energy expenditure, even in less controlled settings. In practice, individualized regression equations are often used to estimate energy expenditure from heart rate, taking into account factors such as age, weight, fitness level, and sex. Accelerometers are currently among the most widely used objective tools for measuring physical activity. They are commonly applied in large national surveillance studies, such as National Health and Nutrition Examination Survey, NHANES, as well as in many types of physical activity research. Traditional research-grade devices, such as actigraph monitors, typically contain a single accelerometer, and users cannot view real-time data during wear. In contrast, modern consumer devices are now widely available and commonly include built-in accelerometers. This includes smartphones and wearable fitness trackers. Although there are many different devices, they generally operate in similar ways. Accelerometers are most often worn on the waist, but they can also be worn on the wrist. Earlier models measured movement in a single dimension, whereas most modern devices capture three-dimensional acceleration along the X, Y, and Z axes. These devices record raw acceleration signals, which are then filtered, integrated, and rescaled during data processing. A key challenge is that different manufacturers use proprietary algorithms to process these signals. As a result, outputs are often device-specific and reported in arbitrary units known as counts, rather than standardized units such as gravitational force. Accelerometers have several advantages. They can be worn over multiple days and are relatively easy to use, with less burden compared to chest strap heart rate monitors. Many devices can store data for 30 to 60 days. They are also relatively affordable, typically ranging from $150 to $500, and provide a more accurate measure of physical activity in free living settings. In fact, accelerometry is considered the gold standard for objective PA measurement in research, and it is often expected in high-quality studies. However, there are some limitations. Accelerometers cannot capture all types of activity. For example, upper body movements like throwing, climbing, or wrestling may not be well detected, especially with hip-worn devices. Estimating energy expenditure from accelerometer data is also challenging. While they perform well for continuous activities, they are less accurate for intermittent, lifestyle-type activities. Compliance can also be an issue. Participants may not wear the device consistently. For example, children may report wearing it all day but remove it during sports. Researchers often apply screening criteria, such as identifying long periods of zero activity, such as 60 minutes, to detect non-wear time. Overall, using accelerometers, especially with children, requires careful data processing and consideration of these challenges. To summarize, accelerometers have strong potential for use across a wide range of populations. They can serve as primary outcome measures in smaller studies, and they are also increasingly used in larger intervention studies with hundreds of participants. In addition, accelerometers can serve as criterion measures to validate other instruments, such as self-report methods. In recent years, there has been growing interest in consumer physical activity monitors. These devices typically use accelerometry, and many also incorporate photoplethysmography sensors and built-in GPS to estimate activity. Fitbit and Apple Watch are among the leading devices in this market. They can track multiple dimensions of physical activity, including heart rate, active minutes spent in moderate to vigorous activity, steps, and distance, estimated using step counts or GPS. Some devices can also provide contextual information by using machine learning to recognize types of activity, as well as track floors climbed and time spent in different heart rate zones. In addition, they estimate calories burned, including both basal metabolic rate and activity-related energy expenditure. Unlike traditional research-grade accelerometers, consumer devices provide real-time feedback, allowing users to monitor their progress directly on the device or through a smartphone app. This makes them more engaging and easier for the general public to understand. In addition to accelerometers and consumer monitors, another commonly used device is the ActivePal. The ActivePal is a small, lightweight device typically worn on the thigh. It uses accelerometry to detect body posture and movement. One key advantage of ActivePal is that it can accurately distinguish between sitting/lying, standing, and stepping, which makes it especially useful for measuring sedentary behavior. Unlike hip-worn accelerometers, ActivePal focuses more on posture-based classification, allowing researchers to assess not only how much people move, but also how much time they spend sitting versus standing. It can also provide information on step counts, transitions, such as sit to stand, and time spent in different postures, making it valuable for studying sedentary patterns. The device is often attached to the thigh using adhesive. Thus, it can be worn continuously for multiple days, including during sleep and water-based activities. However, there are some limitations. It may be less informative for measuring activity intensity compared to traditional accelerometers. In addition, wearing the device on the thigh may cause compliance issues or discomfort for some participants. Direct observation is an objective method used to capture physical activity, particularly useful for children's intermittent activity patterns. Although it can be applied to other populations, it is most commonly used in children and youth. Direct observation is a data collection approach rather than a single technique or instrument. It does not require active participation from individuals. Instead, trained observers record participants' activities in real time. This method can provide both quantitative and qualitative information, including activity levels, as well as contextual factors such as where and when the activity occurs, the environment, and even weather conditions. This is an example of a recording sheet used in System for Observing Play and Leisure Activity in Youth. In this protocol, observations are typically conducted at set intervals, for example, every 3 minutes. The condition section includes several categories. A indicates the area is accessible, U means the area is usable for physical activity, S indicates the area is supervised by staff or personnel, O represents organized physical activity taking place, and E indicates that equipment is available, such as balls or jump ropes. Observers then count the number of boys and girls engaged in different activity levels: sedentary, walking, or vigorous activity. Finally, in the ACT column, observers record the most prominent activity occurring in that area for both boys and girls. Direct observation techniques have been used primarily with children and youth. As an objective method, they are often considered a strong criterion measure for validating other tools, such as self-report instruments or accelerometers. However, like other measurement methods, direct observation has limitations. One issue is reactivity. If children are aware they are being observed, they may change their behavior, such as becoming more active. In addition, this method requires substantial training and practice to ensure observers achieve good reliability and validity. It is also time-intensive and labor-intensive, making data collection potentially tedious and impractical for large sample sizes. To summarize, direct observation is one of the most common and useful methods, and is often considered a gold standard measure. It allows researchers to objectively quantify and code what children actually do during specific time intervals, such as recess or physical education classes. Direct and indirect calorimetry provide very accurate measures of metabolic energy expenditure. These methods can capture most dimensions of physical activity, such as frequency, intensity, and duration, although they do not directly capture the type or context of activity. Direct calorimetry measures energy expenditure by assessing heat production from the body, typically in a controlled chamber. Indirect calorimetry, such as portable metabolic cart, on the other hand, estimates energy expenditure by measuring gas exchange, specifically oxygen consumption and carbon dioxide production. Because the body requires oxygen to produce energy, we can use these measurements to estimate how much energy is being expended. Direct and indirect calorimetry are among the most accurate methods for assessing energy expenditure. However, they are typically limited to laboratory and highly controlled settings, which means they cannot capture real-world physical activity patterns. The equipment is expensive and requires specialized expertise to operate and process the data. It can also be invasive and uncomfortable. For example, participants may need to stay in a metabolic chamber or wear a mask for extended periods. As a result, these methods are often used to validate field-based measures, such as accelerometry, or to develop algorithms for estimating energy expenditure. Doubly labeled water is considered the gold standard, non-invasive method for measuring total daily energy expenditure in free living conditions, typically over 1 to 2 weeks. This method works by measuring total carbon dioxide production. Participants consume water labeled with stable isotopes, deuterium and oxygen-18, and the difference in their elimination rates is used to estimate energy expenditure. From this, we can calculate physical activity energy expenditure by subtracting basal metabolic rate and the thermic effect of food from total daily energy expenditure. One major advantage is that doubly labeled water provides the most accurate estimate of total energy expenditure in real-world settings. However, the main limitation is cost. This method is very expensive and requires specialized equipment and expertise, which limits its use in large-scale studies. To estimate physical activity energy expenditure, we typically calculate it by subtracting basal metabolic rate and the thermic effect of food from total daily energy expenditure. So the key question is, how do we determine BMR? There are two main approaches. The first is direct measurement, usually using indirect calorimetry. This method measures oxygen consumption and carbon dioxide production under controlled conditions, such as fasting and complete rest. It is the most accurate approach, but it requires specialized equipment and laboratory settings. The second approach is prediction using equations, based on variables such as age, sex, height, and weight. Common examples include the Mifflin-St. Jeor equation. This method is much more practical and widely used. You can also use the link provided to estimate your own basal metabolic rate. However, these two approaches can differ in accuracy. Larger discrepancies tend to occur in certain populations. For example, individuals with unusual body composition, such as very high muscle mass or high body fat, may not be well estimated by prediction equations. Protein, carbohydrates, and fats are the primary contributors to the thermic effect of food because they require energy to be digested, absorbed, and metabolized, particularly protein, which has the highest thermic effect. Fiber is generally not included in these calculations because it is largely indigestible and provides minimal usable energy. Here is a link you can use to estimate the thermic effect of food. The next couple of slides will discuss the outcome measures of PA from different method. Because different measurement techniques are based on different principles, such as physiological measures, heart rate, biomechanical measures, accelerometers, and biochemical measures, indirect calorimetry, they produce raw data that are not directly comparable. Therefore, an important step is to convert these raw data into comparable outcomes. For example, step counts from a pedometer are not directly comparable to heart rate data. However, we can apply common criteria to make them comparable. For instance, achieving 10,000 steps per day may be considered meeting physical activity guidelines, while accumulating at least 30 minutes per day with a heart rate above a certain threshold, such as 110 BPM, may also indicate moderate physical activity. By translating different measures into comparable benchmarks, we can meaningfully compare results across different devices and methods. Before computing outcome measures, it is important to first determine what information you want to capture. One key aspect is the type of physical activity. When designing programs or interventions, it is important to understand which activities are most popular and feasible for the target population. For example, if you are working with the city council to plan new infrastructure, such as building a park or adding sidewalks, you need to understand the context of physical activity, including when and where it occurs. However, capturing contextual information can be challenging and is typically only available through self-report or direct observation methods. Because of these challenges, research has traditionally focused more on quantifying the amount of physical activity, such as whether individuals meet physical activity guidelines. Energy expenditure is also particularly important in contexts like weight management programs. In general, investigators are interested in two main aspects: the type of physical activity and the amount of physical activity. To quantify the amount, we typically consider intensity, duration, and frequency. In the case of resistance exercise, frequency is often the primary component used to determine whether individuals meet physical activity guidelines. However, traditional pedometers cannot help track the frequency of doing physical activity. With accelerometers, it is relatively easy to obtain information on the frequency, such as how often activity occurs throughout the day. For heart rate monitoring, the frequency of moderate intensity activity bouts depends on the selected cut point for heart rate, meaning results can vary based on how intensity thresholds are defined. There are different thresholds or cut points used to classify physical activity intensity, such as heart rate, activity counts, or step rate. For self-report measures, intensity is typically estimated using absolute MET values for different activities, or by categorizing activities into intensity levels. Step rate refers to the number of steps taken within a given time interval. For example, about 100 steps per minute is commonly used as a cut point for moderate intensity activity. For accelerometers, moderate intensity activity is defined using count-based cut points, with the lower threshold typically ranging from about 1,000 to 5,000 counts per minute, depending on the device and calibration method. There is no true gold standard for measuring physical activity, as all methods have limitations. For example, doubly labeled water provides an accurate estimate of total energy expenditure, but does not capture activity intensity or frequency. Indirect calorimetry is highly accurate, but is limited to laboratory settings and cannot assess free living activity. Because each method relies on different principles, such as heart rate, oxygen consumption, or activity counts, the agreement across methods is often limited. As a result, there is no direct way to equate data from heart rate monitors, accelerometers, self-report measures, or step counts. At last, we will discuss a few guidelines on how to select appropriate measurement methods. When selecting a physical activity measurement method, the first step is to choose an approach that aligns with your research question. For example, are you interested in measuring intensity, energy expenditure, or simply movement? Different tools are better suited for different purposes. The second step is to select an appropriate outcome measure. The outcome should reflect the specific dimension of physical activity you want to study, such as frequency, intensity, duration, or energy expenditure. For instance, you might use minutes of moderate to vigorous activity, step counts, or absolute or relative energy expenditure, depending on your research goal. Overall, the key is to match both the measurement method and the outcome to the specific question you are trying to answer. When selecting a physical activity assessment method, there is no one-size-fits-all solution. The best choice depends on several key factors related to your research goals and constraints. First, study size matters. Large surveillance studies usually rely on self-report because it's low cost, while smaller or mechanistic studies can use more precise tools like accelerometers. Second, consider the study population. For example, children tend to have more sporadic activity and may not report accurately, so objective measures are often preferred. Third, think about the study design. Cross-sectional studies often use simpler methods, while prospective cohort studies need more reliable tools over time. Finally, your study outcome is critical. If you care about energy expenditure, you need more precise measures, such as indirect calorimetry. If you're just looking at activity frequency, simpler tools may be enough, such as consumer monitors. Finally, I'll show you a summary table of the different measurement methods. I won't go into detailed explanations here, so please take some time to review it on your own.